Programming of process experiment tools is quite easy. First things I have to do is to add my tool into DCU file. DCU file contains definitions of process experiment tools. I have here in the basic toolbox that I have two tools defined. Process experiment procedure, definition is here of the tool, and Ziegler-Nichols tuning, the definition is here. What needs to be defined are these fields. First field is title. I define the title of the tool, and this title will appear here in this selector. Next, I have to decide if I want to use process experiment procedure window. If I write here yes, after clicking on launch, this window will appear and user will be able to define first an experiment of the tool. If I decide no, like in the case of Ziegler-Nichols tuning, after clicking on launch, the window will not appear, but user or designer or programmer will have to define its own interface for his tool. So this is the main difference. There are two ways how to define the tool. Either the tool will use the window for definition of experiment tools or not, and in this case the experiment will have to be defined inside the function. I will show later. Next is description. This description is quite useful. This description appears immediately after clicking on launch. So here the designer can describe to eventual user what the tool will do and how to define, for example, experiment to have successful result. Finally, this field processing tool contains calling sequence of the tool. In process experiment procedure, you see here calling this function. This function will only display the results. In case of Ziegler-Nichols tuning, we have this calling sequence. So we call some Ziegler-Nichols function and parameters online elements. This parameter can be used. It will automatically have a structure inside which is actually selected element from this list. We use it for Ziegler-Nichols to take the control function of the PID controller. So a definition of a new tool is quite easy. I just copy last tool, place it here, define a new tool, define the name of the new tool, decide if I want or not using the window, then some description, and finally I have to have a function that will be called and here I have to change the index. That's all. My new tool is defined, but I have to create obviously this function which will do all the tool needs to do. I open now the Ziegler-Nichols to see how it is defined. So first of all, I check the input parameters, which are selected online elements. I check if it's empty. If it's empty, obviously user have to define select a PID controller. If it's not empty, I check if the functions are not empty. If they are empty, again I need a PID controller to do tuning on. I can also check how many control functions are selected, if more than one. I can also check variables. Some control design tools may need variables to be selected, not control functions. I do not use it here. So I can also check the field output variables. And now I take the control function which was selected like this, and I check if my control function type is RST controller, because PID controllers are in fact simple RST controllers. If not, again I'm not satisfied and I finish. Here I can also check output variables if needed. I don't use it here, but I can check if it's a real variable, binary or integer, for example. Checking is finished. I can do user specification of the tuning method. Here I ask for amplitude of the step and for response time. So this is definition of parameters of my tool. There are some auxiliary parameters computed, so step delay, output variable ID, and so on. And now I can build my process experiment specification structure. Because I do not use my window, I have to do it by myself. So I define the structure like this. It's shown that I have constant overrides, dynamic overrides, and recorded variables, as it's visible in the specification window. Now I define the signal structure, and I can define my constant override. If I want another one, I create another one and replace one with 2. I can do dynamic overrides. I don't need dynamic overrides in case of Ziegler-Nichols. And finally, recorded values. I define recorded values which I need for my experiment. I have to make global the variables that will contain these recorded variables. These are the signal names. I have to make them global, because if in simulation the user must supply these values, these variables. Now I can launch an experiment. It's simple, calling this function which has as input this structure I have defined here. After the experiment, I can work with the data, with the recorded values. So you see I have taken these variables. They should already contain recorded values, recorded signals. And I'm processing the result. I'm computing the tangent. From tangent I'm computing the PID coefficients and display them. Another way how to build process experiment tool is to use the window as I showed before. Process experiment procedure. In this case it's much simpler, because the entire procedure is defined in this window, and after clicking start the experiment is launched, and after the experiment this processing tool calling sequence is called. In this case it's this function. This function is extremely simple. It only displays the recorded values. We can see it here. This simple function I call global this structure. In fact, this structure is created by this window, and it contains constant overrides, dynamic overrides, as well as recorded values. I check the size of the recorded values to display all recorded values. Now what I need, I just get a structure of control variable, actual control variable. I make global the signal that should contain the recorded signal. I put it into the variable sig. I create X and Y and I display it. That's all. Notice that this variable contains again the fields times and values which contain the signal.